Okay, my name is Leah Charity-Spriggs, and this is Physics 2 Lab 3 Circuits. So, in this lab, we used circuits to analyze DC or direct current and RC or resistor capacitor circuits by applying physics principles like loop and node rules. Our main result was that the current in the DC circuit was 0.02 amps and the RC value was 5.99. Our system was the current and its charges, while our surroundings were our apparatus, or the wires, ammeters, voltmeters, resistors, conductors, etc. So for some principles that are important for this lab, loop rule or conservation of energy are these first two equations. Delta V equals the sum of the volt of the resistors, which is equal to the sum of I times R. Then for the capacitor, it's the sum of Q over C. For node rule or conservation of charge, we have I in is equal to I out, or I in minus I out equals 0. Then our third principle is the RC constant starts with the loop rule of a circuit with a resistor, wow, I spelled that wrong, and capacitor. Q over RC plus dQ or dt equals 0, which then gives us delta V equals delta V naught e to the negative t over RC, which then gives us ln delta V over delta V naught is equal to negative t over RC. These are just important equations that you should use in this lab. Okay, so for a DC circuit, I predicted a 0.02A for the current in both ammeters, and the ammeter reading was the same when connected in reverse or backwards. When the voltmeter was connected, we had 3.0 volts and 0.0 amps, so the voltmeter had a strong resistance. Okay, again for our DC circuit, when we took a look at our graph, we started with 0 volts, and as we went through the circuit, we saw the difference in voltage. But as you add the voltage among the entire circuit, you're going to get 0. Like here we have from A to B, it's 3 volts. From B to C, it's 0. From C to D, it's negative 0.96. From D to E, it's 0. From E to F, it's negative 2.04. F to G is 0, G to H is 0, and H to A is 0. So in total, 0. Okay.
I'll fill it up minutes and seconds. It'll be around the same time.
For the RC circuit, when your battery was present, your light was present. Once the battery was removed, the capacitor discharged, the light slowly faded away. For the 10 ohm bulb, it took 13 seconds to charge and 26 seconds to discharge, while for the 20 ohm bulb, it took 25 seconds to charge and 51 seconds to discharge.
There's no potential.
So,
All the potential circuits over the.
yeah, but yeah.
Well, there's no more.
As for possible error, it could be inaccurately reading the voltage or time on the voltmeter or ammeter, which is just a user error. And then for instrumental errors, it could just be an old or broken voltmeter / ammeter. Okay. What if you charged a capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Use an ammeter to measure how long it takes to charge the capacitor when connected directly to the battery and the ammeter. Discuss why the measured time is different from the predicted time. Okay, if we use our model, delta V equals delta V naught e to the negative t over RC, which is one of those equations that I gave in the beginning, you can predict the capacitor to reach full charge in milliseconds. In real life, the result would likely be the same, though it would take slightly longer since wires could produce some resistance and slow the current. That's it.